a properly functioning grounded delta-Y transformer configuration, the line to ground voltages should be equal, typically around 480 volts. However, when the grounding is compromised, these voltages can become unbalanced. In the described situation, the high resistive grounding, or HRG, on the delta side of the first transformer is suspected to be open. This leads to an ungrounded system, effectively creating a floating voltage scenario. The observed unbalanced voltages, specifically 550 volts, 770 volts, and 950 volts, are likely due to several contributing factors. One significant factor is capacitive charging. In a floating voltage system, capacitances exist between the conductors and ground. These capacitances can cause a buildup of voltage, a phenomenon known as capacitive charging. As the capacitance increases, the voltage in the conductors can rise, leading to the observed higher voltage readings. Another crucial aspect is the interaction with a parallel ungrounded transformer. The second transformer, which is also ungrounded, has a ground fault on its phase. This fault provides a low impedance path for current to flow, which can significantly influence the voltages on the paralleled system. The reported 5 volts line to ground voltage on the phase of the ungrounded transformer suggests that current is indeed flowing through this fault, further contributing to the voltage imbalances. While delta to Y transformers are generally designed to minimize circulating currents, it's possible that small circulating currents are present due to imperfections in the transformers or imbalances in the load. These currents can introduce additional voltage distortions, exacerbating the unbalanced line-to-ground voltages. In summary, the high line-to-ground voltages are likely a consequence of the ungrounded system, the capacitive charging effects, and the interaction with the parallel ungrounded transformer. It is imperative to understand that floating voltage systems are inherently unstable and can pose electrical hazards. Therefore, a thorough inspection of the transformers is recommended. Firstly, the HRG should be repaired or replaced to restore proper grounding. Secondly, the system should be re-grounded to re-establish normal and safe voltage conditions. Addressing these issues will significantly improve the stability and safety of the electrical system. It is important to note that working with ungrounded systems can be dangerous, and qualified personnel should perform all inspections and repairs. Safety procedures must be strictly followed to prevent electrical shock and other hazards. Capacitive charging is the phenomenon where electrical conductors act as capacitors, storing electrical energy when a voltage difference exists between the conductor and a reference point, such as ground. This effect is more pronounced in ungrounded systems because there is no direct path for the stored charge to dissipate. The capacitance is formed by the conductors, the insulation surrounding them, and nearby grounded objects. When a voltage is applied, charge accumulates on the conductor, creating an electric field. If the system is grounded, this charge can easily flow to ground, maintaining a stable voltage. However, in an ungrounded system, the charge has no immediate path to ground, causing the voltage to rise until it reaches a point where it can discharge through other means such as arcing or insulation breakdown. This is why ungrounded systems can exhibit erratic and unpredictable voltage behavior. Another factor that can contribute to capacitive charging is the presence of harmonic currents in the system. Harmonic currents are currents with frequencies that are multiples of the fundamental frequency, typically 60 Hz in North America. These harmonic currents can exacerbate capacitive charging because they have higher frequencies, which means they can charge the capacitance more quickly. In addition, harmonic currents can cause increased heating and stress on electrical equipment, further compromising the system's stability. To mitigate the effects of capacitive charging in ungrounded systems, it is essential to maintain good insulation and minimize harmonic currents. Insulation should be regularly inspected and replaced if it shows signs of damage or degradation. Harmonic currents can be reduced by using filters or other mitigation techniques. Grounding provides a low impedance path for fault currents to flow back to the source, which allows protective devices such as circuit breakers to quickly detect and interrupt the fault. This helps to minimize damage to equipment and reduce the risk of electrical shock. In an ungrounded system, there is no direct path for fault currents to flow, which means that protective devices may not operate as quickly or effectively. This can lead to more extensive damage to equipment and increase the risk of electrical shock. In addition to providing a path for fault currents, grounding also helps to stabilize the voltage in the system. Grounding provides a reference point for the voltage, which helps to prevent voltage fluctuations and imbalances. This is particularly important in systems with sensitive electronic equipment, which can be damaged by voltage variations. In an ungrounded system, the voltage can float, which means that it can vary significantly from ground potential. This can cause erratic behavior and damage to electronic equipment. There are several different types of grounding systems, each with its own advantages and disadvantages. One common type of grounding system is the solidly grounded system, in which the neutral point of the transformer is directly connected to ground. This type of system provides a low impedance path for fault currents, which allows protective devices to operate quickly and effectively. However, solidly grounded systems can also be subject to high fault currents, which can cause damage to equipment. Another type of grounding system is the high-resistance grounded system, in which a resistor is placed between the neutral point of the transformer and ground. This type of system limits the fault current, which reduces the risk of damage to equipment. However, high-resistance grounded systems may not provide as much protection against electrical shock as solidly grounded systems. The choice of grounding system depends on the specific application and the requirements of the electrical system. Factors to consider include the size of the system, the type of equipment being used, and the level of protection required. It is important to consult with a qualified electrical engineer to determine the appropriate grounding system for a particular application. When troubleshooting voltage imbalances in an ungrounded system, it is important to first verify that the grounding system is properly installed and functioning. Check the grounding connections to ensure that they are tight and free of corrosion. Measure the resistance of the grounding system to ensure that it is within acceptable limits. If the grounding system is not functioning properly, it should be repaired or replaced. Once the grounding system has been verified, the next step is to identify the source of the voltage imbalance. This can be done by measuring the voltage at various points in the system. If the voltage is significantly different from ground potential at any point, then there is likely a fault in that part of the system. The fault could be caused by a variety of factors, such as damaged insulation, loose connections, or faulty equipment. Once the fault has been identified, it should be repaired or replaced. After the fault has been repaired, the voltage should be measured again to ensure that it is now within acceptable limits. It is also important to regularly inspect and maintain the electrical system to prevent future voltage imbalances. This includes inspecting the insulation tightening connections and testing equipment. By following these steps, it is possible to troubleshoot and correct voltage imbalances in ungrounded systems. Remember that working with electrical systems can be dangerous, and it is important to follow all safety precautions. If you are not qualified to work on electrical systems, then you should consult with a qualified electrician. The interaction between parallel transformers can be complex, especially when one or both transformers are ungrounded or have grounding issues. When transformers are paralleled, they share the load, and their voltages and currents are interconnected. In a properly functioning system, the transformers should have similar voltage ratios, impedances, and grounding configurations. However, when these parameters are not matched, circulating currents can occur between the transformers, leading to voltage imbalances and other problems. In the described scenario, the two transformers have different grounding configurations. One transformer has a high resistance ground, while the other is ungrounded with a ground fault on the phase. This difference in grounding can cause significant circulating currents to flow between the transformers. The circulating currents can cause the voltages to become unbalanced as the currents flow through the impedances of the transformers and the connected loads. The circulating currents can also cause increased heating and stress on the transformers, which can shorten their lifespan. To mitigate the effects of circulating currents in parallel transformers, it is important to ensure that the transformers have similar voltage ratios, impedances, and grounding configurations. The transformer should also be properly sized for the load, and the load should be balanced as much as possible. If the transformers have different grounding configurations, it may be necessary to isolate them from each other using isolation transformers or other means. Another important consideration is the transformer impedance. The impedance of a transformer is a measure of its opposition to the flow of alternating current. Transformers with different impedances will share the load unevenly, which can lead to circulating currents and voltage imbalances. To ensure proper load sharing, the transformers should have impedances that are within a certain tolerance of each other. The tolerance will depend on the specific application, but it is typically in the range of plus or minus 10%. In addition to the transformer impedance, the impedance of the connecting cables can also affect the load sharing. The cable should be sized appropriately to minimize voltage drop and ensure that the transformers share the load evenly. Another factor to consider is the transformer tap settings. Transformers have tap settings that allow the voltage ratio to be adjusted. If the tap settings are not properly adjusted, the transformers will not share the load evenly. The tap settings should be adjusted so that the voltages on the transformers are as close as possible to each other. It is also important to consider the transformer cooling. Transformers generate heat as they operate, and they must be properly cooled to prevent overheating. If the transformers are not properly cooled, they can overheat and fail. The cooling system should be designed to provide adequate cooling for the transformers under all operating conditions. Troubleshooting a system with parallel transformers can be complex, and it is important to have a thorough understanding of the system. It is also important to have the proper tools and equipment, such as a voltmeter, an ammeter, and an impedance analyzer. The first step in troubleshooting is to verify that the transformers are properly connected and that the grounding system is functioning properly. Check the connections to ensure that they are tight and free of corrosion. Measure the resistance of the grounding system to ensure that it is within acceptable limits. If the grounding system is not functioning properly, it should be repaired or replaced. Once the grounding system has been verified, the next step is to measure the voltages and currents on the transformers. Compare the voltages and currents to the expected values to identify any anomalies. If there are any anomalies, then there is likely a fault in the system. The fault could be caused by a variety of factors, such as damaged insulation, loose connections, or faulty equipment. Once the fault has been identified, it should be repaired or replaced. After the fault has been repaired, the voltages and currents should be measured again to ensure that they are now within acceptable limits. It is also important to regularly inspect and maintain the transformers to prevent future problems. This includes inspecting the insulation, tightening connections, and testing the cooling system. By following these steps, it is possible to troubleshoot and correct problems in systems with parallel transformers. Working with electrical systems can be dangerous, and it is important to follow all safety precautions. If you are not qualified to work on electrical systems, then you should consult with a qualified electrician. Ground faults can be particularly problematic in ungrounded systems. In a grounded system, a ground fault is a direct short circuit between a phase conductor and ground. The fault current flows back to the source through the grounding system, causing a large current to flow. This large current trips the circuit breaker, quickly disconnecting the faulted circuit and preventing further damage. In an ungrounded system, there is no direct path for the fault current to flow. Instead, the fault current flows through the capacitances between the conductors and ground. The fault current is typically much smaller than in a grounded system, and it may not be large enough to trip the circuit breaker. This means that the fault can persist for a long period of time, causing damage to equipment and increasing the risk of electrical shock. Another problem with ground faults in ungrounded systems is that they can be difficult to detect. The fault current is typically small and distributed throughout the system, making it difficult to pinpoint the location of the fault. This can make it challenging to troubleshoot and repair the system. There are several methods that can be used to detect ground faults in ungrounded systems. One method is to use a ground fault relay. A ground fault relay is a device that monitors the current flowing in the grounding system. If the current exceeds a certain threshold, the relay will trip the circuit breaker, disconnecting the faulted circuit. Another method is to use a high-resistance grounding system. In a high-resistance grounding system, a resistor is placed between the neutral point of the transformer and ground. This limits the fault current, making it easier to detect and trip the circuit breaker. It is also important to regularly inspect and maintain the electrical system to prevent ground faults from occurring. This includes inspecting the insulation, tightening connections, and testing equipment. By following these steps, it is possible to minimize the risk of ground faults in ungrounded systems. Remember that working with electrical systems can be dangerous, and it is important to follow all safety precautions. If you are not qualified to work on electrical systems, then you should consult with a qualified electrician. The National Electrical Code, or NEC, provides guidelines for grounding electrical systems. Section 250.20 discusses general requirements for grounding and bonding. It states that electrical systems must be grounded in a manner that prevents voltage from exceeding certain limits. Section 250.21 covers systems that are not required to be grounded. These systems are typically small, isolated systems that do not pose a significant risk of electrical shock. Section 250.24 specifies the requirements for grounding separately derived systems such as transformers and generators. It requires that these systems be grounded in the same manner as other electrical systems. Section 250.30 covers grounding electrode systems. It specifies the types of grounding electrodes that are permitted, such as metal underground water pipes, metal frames of buildings, and ground rods. Section 250.50 specifies the requirements for bonding electrical equipment. Bonding is the process of connecting all metal parts of an electrical system together to create a low-impedance path for fault currents. Section 250.166 provides requirements for high-impedance grounded neutral systems. There are specific requirements listed. For example, the neutral conductor shall be insulated for at least 600 volts. The NEC also contains requirements for specific types of equipment and applications. For example, Article 517 covers healthcare facilities, and it contains requirements for grounding and bonding in those facilities. Article 690 covers solar photovoltaic systems, and it contains requirements for grounding and bonding in those systems. It is important to consult the NEC for specific requirements related to grounding and bonding. The NEC is a complex document, and it is important to have a thorough understanding of it before working on electrical systems. It is also important to consult with a qualified electrical engineer to ensure that the electrical system is properly grounded and bonded. The information provided here is for general guidance only, and it should not be used as a substitute for professional advice. It is important to consult with a qualified electrical engineer to ensure that the electrical system is properly designed, installed, and maintained. The information is not a substitute for the NEC or other applicable codes and standards. It is important to consult the NEC and other applicable codes and standards before working on electrical systems. Working with electrical systems can be dangerous, and it is important to follow all safety precautions. If you are not qualified to work on electrical systems, then you should consult with a qualified electrician.